Okay, another old exam question here, and let's just dive right in. This is from the same old exam. This is again from 1920 fall, exam 3. I'll just click it a little further along. This is number 4. Okay, so this is a question about inner product spaces, and this is a question designed to kind of walk students through a very important real-world application, which I think makes it a fun question and also a great topic for discussion here. So we're going to think of, we've seen lots of different kinds of inner product spaces. I'm going to think of an inner product space of photographs, which seems like a weird thing to do, but it turns out, if you think about it, I mean, what is a photograph? A photograph means that every point in a rectangle, typically, there is a associated real value. I'm thinking of grayscale photographs. If color, it's maybe multiple real values, red, green, blue, something like that. Let's not worry about that. So grayscale photograph, how bright is that 1 pixel, right? It's a real value that you associate to each point on a rectangle, so it's a real valued function on a subset of R2, and that is certainly a vector space, and we're going to think of it as an inner product space using the L2 inner product. Okay. All right. So with that point of view, I'm going to assume now that we have an orthogonal basis for whatever this inner product space is, and that's a whole topic of discussion of which orthogonal basis and why, and what are the various benefits of different orthogonal bases. And so I don't want to get into that. That's too much, but a lot of really interesting and powerful ideas in that question. We're just going to assume that we have an orthogonal basis. Okay, and specifically, we're going to focus on 2 of the vectors in that orthogonal basis, calling them F and G. So lastly, we're going to be thinking about a specific actual photograph that we're interested in understanding, in compressing, and we're going to call that photo H. The way we're going to understand H is by understanding it as being a linear combination of F and G. So I want to start off by assuming that the photo is in the span of F and G. Now, in reality, it's going to be more complicated than that. What are the odds that a photograph that I take is going to just happen to be a linear combination of exactly 2 of the vectors in my orthogonal basis? Nah, probably not, right? It's probably going to be a combination of many of them. Just because, I mean, again, there's a very high dimensional inner product space, and so it's probably going to have coordinates all over the place. But just to keep the algebra simple, and the nugget ideas of what I'm interested in describing here works just as well if I think of it as a combination of 2 only. So just this is just a sort of a simplification, but it's just in the sense that we're going to look at 2 functions instead of many. But the algebra would be identical otherwise. Okay, another complication while we're at it. Very likely, the photograph that we would take and want to write as a combination of simpler images actually isn't technically actually a combination of all of them, even all of them, but close. Right, so that's a whole nother thing. So the idea of how we would use an approximation to approximate the photo. How would I use a linear combination to approximate a photo? Not far off from what we're doing, but not something we're going to talk about here. Okay. All right, so this is a linear combination of those. And now I'm given here, again, some free information. Why I want this information, I'm not going to say yet. We'll refer to it as needed as it comes up in the process that I'd like to do. If we need some of this information, we'll come back for it. Okay, so I want to, as it says here, view H as a linear combination of F and G. Specifically, want to find those coefficients. All right, so I'm going to be using here one of the big theorems from section 9.2. And excuse me, so that is the theorem that says if you have an orthonormal basis, then coordinates, namely coefficients in a linear combination, right? Coordinates are components, projections sometimes, namely computed with inner products with those orthonormal basis vectors. So that's a huge theorem. That's going to be, ultimately, that's what's going to give us the answer to this question. But do notice we have to start off by observing that that requires having an orthonormal basis. We do not currently have an orthonormal basis. We have an orthogonal basis for the span in question. These vectors are not unit vectors. So I need to take these vectors f and g, and I need to divide them by their own magnitudes. And to do so, of course, I need to know their magnitudes. And this right here actually tells me what I need, if you think about it. So what this equation here is saying is, this is the definition of magnitude squared. So magnitude squared of f is 4, and that means that the magnitude of f is 2. Okay, and then likewise, this tells me that the magnitude of g is 3. So there. So dividing f and g by their own magnitudes means divide f and g by, well, 2 and 3 respectively, and that gives me then a new basis. U1, U2 is what I'm going to call them, and that is an orthonormal basis for this span that we're interested in. All combinations of f and g. Okay, so that's the first part of the problem. Realize we need an orthonormal basis, and then get it. And notice we've used some of the given information. Okay, so here's where we can then actually sort of do the real nugget, the real work of this question. There's this function here that I want to write as a linear combination. Well, I want to write it as a combination of f and g, but yeah, again, f and g are kind of hard to deal with. Let's not deal with f and g. They're not an orthonormal basis. Let's deal with u1 and u2, being as they are an orthonormal basis. And so I'm going to look at these vectors here, try to write h as a combination of them, because I know that finding those coordinates is easy by way of our powerful theorem, right? These coefficients, the coordinates, are computed with components. The big theorem, one of the first big theorem from section 9.2. Coordinates are components, and components are computed with inner products with unit vectors. Okay. So, right. And so, yeah, but how do I do that though? How am I going to compute these inner products? I need to know the inner product of h with u1 and h with u2. And do I have that? No. What I do have though is inner products of h with f and g. And so my goal, in order to be able to figure out how to compute these, is to try to relate inner product of h with u1 with inner product of h with f. And conveniently, that's no big deal, right? I mean, u1 is very closely connected to f. u1 is, well, it's, by definition, it's f over 2. So I write that down and factor out this factor of a half. And all of a sudden, I've got exactly the information that I have up here, right? Inner product of h with f is 5. And therefore, that first coordinate in yellow here, this first coordinate is 5/2, being as it is 1/2 of that inner product. Okay. And then likewise for U2. Okay. All right, so I've got those coordinates computed. Now it's very tempting to spike the football and declare victory. We found coordinates, right? Coordinates are coefficients. We're looking for coefficients. We found coefficients. Aren't we done? Well, not quite. Really close. I mean, again, we've done the meat of the problem here, but we want H as a linear combination of F and G. What we have found here is H as a combination of U1 and U2. So it's, again, we've got to run the ball in here, the last little bit. Don't spike it on the 2-yard line. Viewing H as a combination of U1 and U2, remember that U1 is F over 2. U2 is G over 3. So these coefficients that I've found of 5/2 and 7/3, when I change the basis back to writing that in terms of F's and G's, the coefficients with respect to the basis I actually care about are 5/4 and 7/9. Okay. All right. So what this means, let me just celebrate a little bit. What this means is if you've got some photograph and in a inner product space of photographs, and if it's a combination of an orthogonal basis that you found, right? Or if it's approximated, if it's very close to something that is a linear combination of the orthogonal basis that you have, and that, by the way, pretty much always the case, then I don't have to store this photograph pixel by pixel, right? That's extremely inefficient. Every single pixel, there's millions, there's tens of millions of pixels. It takes up a lot of data, a lot of space, right? So what you can do instead is say, well, that's inefficient. Look, I'm gonna have these photographs here, F and G, are pat images that are very simple, that I can that I already have. I'm going to store them. They're like my alphabet, right? And I don't have to store all the pixels for this. I can store just these coefficients and say, I'm going to think of H as being these numbers. And then if I ever want to look at the photograph, right? Once I've thrown away all the actual photo and all I have is just these numbers, these coefficients that help me approximate it. If I want to look at the photograph, I just compute up this linear combination and I get, well, the original image. So it's a really powerful idea. This is one of the ideas in image compression, extremely clever. And notice it relies critically on this theorem that says that coordinates are components. Namely, it requires critically on the idea of inner product spaces and inner products, and here specifically the L2 inner product. So I think that's a really interesting question. I hope this has been a useful discussion. By the way, you'll notice in my old exam questions, some highly analogous questions involving Fourier series. Same idea. Instead of viewing photographs as combinations, there we're viewing periodic functions as linear combinations, and it's just a slightly different inner product space, but ultimately a lot of the same ideas. Okay, so hope this has been useful.